So how about diagenesis in environments that are above seawater in basically continental setting? That's known as meteoric diagenesis, and of course this is an environment where a lot of diagenetic transformation can happen, in particular for carbonates. So we can distinguish two main zones in the meteoric environment, and the distinction is based on where they sit with respect to the water table. So first we have the Phreatic zone that is below the water table, and so it's characterized by being saturated with meteoric water. You have water everywhere, and that leads to the deposition of a lot of cement. So we talked about the water-rock ratio and its importance for diagenetic transformation. In the case of meteoric diagenesis, the fluid is rainwater. So how much rain you have will determine how much diagenetic transformation you have. And of course, what controls this is climate. So let's look at what can happen in different climatic regimes. If you are in an arid environment and you're looking at specifically carbonate successions now, you basically form a thin calcrete at the top of your sediment. So that's a thin soil that can form because you have very little water, so you have very little cement in that soil. And then in the vadose zone, because you don't have a lot of water, you preserve both magnesium calcite and aragonite, which are very delicate minerals. Whereas in the Phreatic zone, below the water table, only aragonite and calcite are preserved, but aragonite is preserved. So example of this would be in the Middle East, where you can see that at the surface you have evidence of meteoric alteration of carbonates. This is here a picture I took in Saudi Arabia. But a lot of the sedimentary features are still very well preserved. For instance, here at the surface we have exquisite evidence of biturbation that are of Jurassic age, and meteoric diagenesis has not dissolved this feature. Now, if you're in a semi-arid environment, the calcrete, the zone of evaporation and precipitation of mineral, is much thicker. And notice that in the vadose zone, because we have more water, we now have aragonite and calcite preserved, but magnesium calcite is gone. Whereas in the Phreatic zone, we only have calcite. And at the interface between the two, we're starting to have cave formation. So an example would be Southern Europe, Italy, or Spain, where we have the beginning of what is known as karst landscape, but we still preserve some of the limestones. And finally, if you're in a very wet, humid environment, then you don't preserve any of the aragonite and magnesium calcite. That means in the vadose and Phreatic zone, we have only calcite, and we have extensive dissolution and formation of cave, plus the deposition of a terra rossa soil, which is essentially all the clays that were in the limestone that are concentrated at the top. Beautiful example of this would be in Southeast Asia, like in Vietnam here, where you have this pillar of limestone that are just vestige of all the limestone that was dissolved. You can imagine that all the other limestone was dissolved, and that's because we are in tropical humid conditions. So a lot of dissolution is taking place in that particular landscape. And of course that leads to the formation of caves, of cavities of dissolution, which is a diagenetic transformation classical for limestone in very wet conditions. So hopefully you can see by now that diagenesis plays a big role in controlling how rocks look and how sediment are transformed into rocks. Now in our last class, so the next class, we'll look at the building of a stratigraphic time chart, or how we define the geological time period.